Okay, next topic is LC circuit. So assume that there are these two, inductor and capacitor, they're connected in parallel. Okay, and at t equal to 0, I'm closing the switch. This is inductor in Henry, capacitor in Farad. Now assume that this capacitor is fully charged. Okay, when it is fully charged. Now what happens when I close the switch? Here, this stored energy, how much energy it has? It has half CV square. That's the energy it has. So the voltage across this must be V. Once I close the switch, what happens? The current is going to go in this direction, I. Actually, that's not a constant current, that varies with respect to the charge here. Okay, so that's the I. Now what happens in the second case? Now all the energy is going to be right here in the magnetic field format. Okay, once I close the switch, now all the energy here, it is 0 joules, because all the energy is transferred to the inductor. Now this inductor has full energy. How much energy does it have? It has half Li square. Here, one assumption I'm making, I'm assuming that this inductor and capacitor, they both doesn't have any resistance. So here our internal resistance is 0 ohms, here internal resistance is 0 ohms. So resistance is the one which consumes energy. It takes electrical energy and convert that into heat energy or light energy. Since they both doesn't have any resistance, here what happens, the losses are 0. So whatever the energy here, it is transferred to the inductor. Now what is the property of the inductor? It does not allow sudden change in current. So previously the current was traveling in this direction, so it will continue traveling in that direction, I. Okay, so again this will start charging. I mean, in the next I should have drawn next one in the next diagram. So now the current is going to be go in the same direction. So now this is going to be positively charged, this is negatively charged. Okay, so now energy is transferred from inductor to the capacitor. So this is a complete one cycle. Okay, after one cycle, now current is changed its direction. So current is going to go in this direction. Again, inductor will energize and this will be discharged completely. And again, in the next step, this plate is going to be positively charged, that plate is going to be negatively charged. Okay, that's how energy is going to transfer between inductor and capacitor. So this LC circuit is, I'm assuming it's a lossless, but in reality the inductor definitely is going to have some resistance. That resistance value equal to R equal to rho L by A. Rho is the resistivity, L is the length of the conductor, A is cross-sectional area of the conductor. So based on this, it's made with a wire, for sure it will have some resistance. Same thing with capacitor. Capacitor also made with two conducting plates, so those conducting plates will have some resistance. So capacitor is going to end up having some resistance. So after a few seconds, the energy is going to be lost through that resistors. But here I'm assuming both of them are pure inductor and pure capacitor. There is no resistance. Resistance is 0. Now can I say that voltage drop across capacitor equal to Q equal to V equal to Q over C, and the voltage drop across the inductor, we call that as, we indicate with E. E is nothing but induced EMF. So that's the reason I'm indicating with E, but V and E are same almost. E equal to minus L times di by dt. Okay, so these two are in parallel, so the both must be equal. So Q over C must be equal to L times di by dt. So basically here this is L times di by dt, this is Q over C for the first part, but these signs are going to reverse for the next cycle. Now I'm going to take I equal to dq by dt. So if I substitute I over there, q over c equal to L times d square q over dt square. Now q across the capacitor, I'm going to take q equal to q naught cos omega t. So what is going on? I mean, why I'm representing this q equal to q naught cos omega t? So q naught equal to maximum charge in the capacitor. Okay, now what is going on? Initially, if you remember, initially across the capacitor I have maximum charge. Once I turn on the switch, that charge is discharged. Okay, so I would say this is 90 degrees. Again, it's going to go in the opposite direction. Okay, now this is complete cycle. Okay, so this is how the charge is going over the capacitor. So first it is fully charged, it will be discharged, again it is going to charge in the reverse direction. So basically this is half cycle. I believe I said that's a full cycle, but that's a half cycle. Again, from here it's going to discharge again it's going to charge again. So if you remember, capacitor has this positive charge and negative charge here. Now in the next few movements it's going to be 0. So here it becomes 0. The next movement it's going to be this one positive, this one negative. Okay, so here I am at 0. At 90 degrees my charge across the capacitor is 0. Now this is at exactly 180 degrees. After 180 degrees, again this one becomes 0. So that is 270 degrees. Again at 360 degrees, this is 360. At 360 degrees, again this is going to be positive, this is going to be negative. So this is 0 degrees, 90 degrees, 180, 270 and 360. So during that time, the charge across the capacitor. Now if I substitute q value in there, so q equal to, I have d square q naught cos omega t over dt square equal to, I'm going to bring this L also the other side. We'll end up with 1 over LC. Q is nothing but q naught cos omega t. Okay. Now we're going to derivate this twice. Once you derivate this twice, we will end up with minus omega square plus 1 over LC times q naught times cos omega t equal to 0. Okay, now to get the omega value, okay, to get the, sorry, here we have two parts. Either this part has to be 0 or this part has to be 0. So we know that at 90 degrees this part is going to be 0. So what if I make this part equal to 0? So omega square plus minus omega square plus 1 over LC equal to 0. So omega equal to 1 over square root of LC. This omega is called angular frequency. So which is nothing but how many rotations, how many times. So this is nothing but one cycle. Okay, so how many times it's going to rotate, or charge is transferred from capacitor to inductor, inductor to capacitor in 1 second. That's what it's going to tell you. So angular frequency, which is radians per second. So how many times it is rotating, how many radians it is rotating in 1 second. Okay, which is nothing but 2 pi f. Omega equal to 2 pi f. You need to remember this all the time. Okay, so here we call this omega naught. So this is called resonance frequency. Okay, so basically this is nothing but omega naught resonant frequency. Resonance, I would say angular frequency, because it's omega, which is 1 over square root of LC. F naught is resonant frequency. Okay, in resonance frequency it's 1 over 2 pi square root of LC. So this is what our in this is in hertz, this is in radians per second. Okay, so this is how the energy is transferred from capacitor to inductor, inductor to the capacitor. Thank you.